Hello friends, welcome. This is Shalini. Today I am going to explain Google File System. Let's start the video. Contents in the video are introduction, design overview, system interactions, master operations, fault tolerance and diagnosis, measurements, experiments, conclusion and references. Coming to the introduction, what is Google File System? Google File System is a scalable distributed file system for large distributed data-intensive applications. GFS is designed by Google for meeting the rapidly growing demands for data processing needs. It shares the same goals as previous distributed file systems, such as performance, like how well it is performing, scalability, like how much amount of data it can handle, reliability, is it trustworthy or not, availability, how easily we can access this. Why GFS chosen over previous file systems? Well, there were many previous file systems. Why people need to use GFS? In the previous file systems, there were many drawbacks. So this Google File System is going to overcome those drawbacks, and especially this is designed to support the distributed applications. Design overview. Assumptions. These are the assumptions we need to keep in our mind while designing the file system, especially for distributed applications. Should be built from inexpensive commodity. We are going to build the file system from inexpensive commodity, so there are chances for failure, occurrence of failure. So the file system should detect the failure, tolerate it, and it should overcome the defect by itself on regular basis. Should store modest number of large files. We expect the file system should store like millions of files whose size will be like 100 MB. That's the smallest size. Workloads. Primarily there are two workloads: large streaming reads and small random reads. Large streaming reads can read like almost hundreds of KBs of data at a time, and small random reads read like typically like few KBs of data. Coming to the sequential writes. Sequential writes, data is appended on sequential writes. Highly sustained bandwidth is more important than low latency. That's one of the assumptions. Design overview. Interface. Google File System provides familiar file system interface. Even though it does not provide a standard API, such as portable operating system interface. Files are organized hierarchically in directions and identified only by the path names here. Google File System supports usual operations, file operations, especially like creating, deleting, open the file, close, read and write. And it is also going to provide two extra operations here: snapshot and record append. Snapshot is used to create a copy of a file or whole directory. We are going to study it in later. Record append. It allows multiple clients to append the data concurrently at the same time, and it guarantees the atomicity of the client appends. It is useful for implementing producer and consumer queues for many clients that are concurrently appending the data at the same time without locking the file. That's the advantage of this record append. Let's see the design architecture. GFS cluster contains only single master and multiple chunk servers which are assigned by multiple clients. It is easy to run both the chunk server and the clients on the same machine until the particular machine doesn't have any problem. Files are divided into fixed number of chunks. Each chunk is handled by the 64-bit chunk handler assigned by the master while creation of chunk. For reliability, chunks are replicated on multiple chunk servers. We store like 3 replicas on the chunk server. Whenever the machine is spoiled or whenever the machine is it's in failure, we can use the replicas at the time. Master maintains only metadata information. Client interacts with the chunk server for write and read operation. Let's now see the mechanism, how it's gonna work in the figure. First of all, GFS client converts the file name and byte offset in a file to file name and chunk index and requests the master with file name and chunk index. The master replies the client with chunk handle and chunk locations, where are the chunks are located in the GFS chunk server. Then the client is going to send the request to the nearest chunks with chunk handle and byte range, like how many bytes it wants to read or write. Once the client interacts with the master, it's going to catch some information. So immediately for further write or read operations, it doesn't want to interact with the master because it has some information with it. Till the information expires, it doesn't want to, no need of asking the master about the information of the chunk, like where is it present, etc. Single master. Every GFS server has only one master. Single master simplifies the design and enables the master to make sophisticated chunk replacement and replication decisions. We must minimize the involvement of the master in read and writes so that it doesn't become a bottleneck. Clients never ask master to read or write data. It asks for what chunk server it should contact. Information like that. Generally, master holds metadata information, mainly the 3 informations like namespaces, access control information, mapping from chunk to files or file to chunks, and the master controls the activities such as chunk lease management, garbage collections, like garbage collections in the sense deleting the old chunks or orphan chunks, chunk migration between the chunk servers, like moving the chunks from one chunk server to the other chunk server. We are going to learn this in the next slides, coming slides. Chunk size. Chunk size is one of the key design parameters in this system. A file is divided into a small sized unit called chunk, and each chunk size is 64 MB, which is greater than a typical file system block size. and each chunk replica is stored as Linux file on chunk server. Lazy space allocation avoids waiting space due to internal fragmentation, perhaps which is the greatest objection for the large chunk size. Why large chunk size? Is it an advantage or disadvantage? Well, there are like few advantages and few disadvantages of this. And here we come to the advantage. Reduces client's need of interacting with the master. Read and write on the same chunk file needs only like one initial request from the master. So the client is going to catch the information. So if the client is working on the same chunk, no need to ask the master again and again, as it will catch the information and it can use the information till it is expired. So it doesn't, no need of interacting with the master again and again. And the second point, reduces the network overhead by keeping persistent TCP connection to the chunk server over an extended period of time. As our applications prefer to read and write on the large chunk sequentially, means it wants to perform read and write operations like for large number of data. So if it's working on the same chunk, there won't be any traffic in the system. So it is one of the advantage. Reduces the size of metadata stored on the master. Master stores it metadata on memory. So if there are only few chunks which are having, or which are going through the operations, which are going through read and write operations, so master is no need of memorizing or keeping log of large amount of data. Like only few chunks are working, it can only keep that amount of chunks in the log, and very few data can be kept, so that the pressure and burden on the master will be reduced. This is one of the advantage of the large chunks. And as well, there is a disadvantage, but we can solve it. What is the disadvantage? Chunk servers storing chunks may become hotspots if many clients access the same data concurrently. Well, this is not a big disadvantage, as our applications mostly read large multi-chunk files sequentially. There won't be like many hotspots forming, so it's not a disadvantage. Let's go to the next slide. Metadata. Metadata contains mainly three types of data: chunk namespace, mapping from files to chunk, location of each chunk replicas. Three of the datas like chunk namespaces, mapping from files to chunk, and locations of chunk replicas are saved in memory, and only the chunk namespaces and mapping from chunk files to chunks are saved in operational log. We are going to see the operational log in the same slide. Master does not keep persistent records of chunk location, instead asks chunk server through a heartbeat message, due to the following reasons. To eliminate the problem of keeping the master and chunk server in sync, because chunk server always leaves and joins the cluster, it will be difficult for them to keep the chunk server and master to keep in sync. The second one is error on the chunk server makes chunk to vanish spontaneously. Even though if the master holds the record of chunks, locations, everything, whenever the chunk server has errors, the data is going to vanish spontaneously. So it will be difficult for the masters to always update the data time to time. So it is better to ask the chunk, because chunk server only knows what chunks are involved in the operations currently and what are not. So it is always better to master to ask the chunk server instead of itself keeping the record. Then coming to the operational log, it contains historical record of critical metadata changes. Whatever the changes happened on metadata should be stored on the operational log. And operational log not only records the changes on metadata, but it also serves as order of concurrent operations. Stored it on master's local disk and replicated on multiple remote machines. Since the operational logs are critical, we must store it reliably and not show it to the clients until all the changes on the metadata are persistent. If once we lose the client's operations like metadata operational log operations, it would be very difficult to get it. So it should be better, master stores one set of its log operations on the local disks and it keeps the replicated ones itself. And to minimize the startup time, we must use checkpoints. To minimize startup time, we must use small logs. We use checkpoints to limit the number of log records. Means checkpoints are used to check like the limit of the log records. So whenever the master is crashed, it needs only the latest checkpoint and subsequent log files, not the old one. So it's better to delete the old checkpoints because it's not in use anymore. Let's go to the next slide. Guarantee by GFS. Consistency model. GFS has a consistency model which supports distributed applications. File namespace mutations are atomic and are always handled by the master. As you see, there are some terminology here like defined, consistent, undefined, and inconsistent. So we are going to learn that. What is consistent? First of all, before that, we need to know what are the what is the state region after the mutation. The state of file region after the mutation depends on what type of mutation it has gone through. So coming to the consistent, what is consistent? If all the clients see the same data, regardless of which replica they read from. If they read from different replicas or they are seeing this like same data, if the client is seeing the same data, then the region is consistent. When it is defined after a file mutation, if it is consistent and clients will see what the mutation writes in it entirely. After a data like manipulation, if it is still consistent, like all the clients see the same data regardless of which replica they are using, and the clients will also see what mutations writes in it entirely, then the state is defined as, state region is defined. Concurrent successful mutations leaves the region undefined. A failed mutation makes the region inconsistent and undefined. Data mutations may be write or record appends. Mostly the data mutations will be record appends. Instead of starting or writing on a fresh chunk, they are going to add the data to already written data. After a sequence of successful mutations, the mutated file region is guaranteed to be defined and contains data written by the last mutation. GFS identifies the file chunk servers through a mutual communication between the master and the other chunk servers, and it is going to delete the failed chunk server, and the master is going to see the corruption of data, like detected the corruption of data by checksumming. So next go to the next slide. Implementation for applications. A GFS applications can accommodate the relaxed consistency model with like few simple techniques as follows. Replying than appends rather than overwriting. Mostly in our applications, the data mutation is done by appending than overwriting. Checkpointing. Checkpointing helps the writer to restart incrementally, and self-validation. Let's go to the next slide. Lease and mutation order. Mutation is the operation that changes the contents or metadata of the chunk. Data mutations can be like write or append data. Each mutation is performed on all chunk replicas. Or whatever the data mutation, it should be performed on all chunk replicas. So we introduce a mechanism called lease mechanism here. So leases are used to maintain a consistent mutation across replicas. Leases are going to help to perform operations like data mutations on all the chunk replicas. The mechanism is as followed. Master grants chunk lease to one of the replicas called primary, which holds only for 50 seconds. The lease is given by a master to one of the chunk replicas, which is called primary, for just 60 seconds. Primary picks a serial order for all the mutations it should undergo, and specifies all the replicas to follow the particular order. Like whatever the order the primary is picking, the replicas should follow the same order. As long as the chunk is being mutated, the primary can ask for time extensions. If the mutations are going on the chunks and the 60 seconds are going to end, means the primary can ask the master for extension of the time. These extensions and requests are piggybacked on heartbeat messages between the master and the chunk server. Let's go to the next slide. Write control and data flow. Here the write control and data flow is explained to this diagram. Step 1. The client will request the master for the current lease of the chunk and locations of all the other replicas. For step 2, the master is going to reply the client through locations of the primary and other replicas. In the step 3, the client pushes all the data to the replicas. The client doesn't follow any rule for sending the data to the replicas or order. Then the chunk server is going to store the data in URL buffer and caches it till it is used or expired. The step 4 is, after all the replicas acknowledge, client sends the write request to the primary. By seeing the request, the primary comes to know that the client has already sent the data to the replicas, and it started to write serialization number for the data mutations from different clients, which provides serialization. In the step 5, primary forwards write request to all replicas and ask them to follow the particular order, particular serial number which the primary is following. In the step 6, the secondaries all reply to the primary, indicating that they have completed the operation according to the serial numbers to the data mutations what primary has given. In the step 7, primary replies to client that if any errors occurred at the replicas ought to be reported to the client. In case of errors, write may succeed at primary and an arbitrary subset of secondary replicas. Let's go to the next slide. Data flow. We decouple the data from flow of control to use the network efficiently. We are using this data flow to use the network properly. For this, we are going to follow a technique. Data is pushed linearly along a chain of chunk servers, especially in a pipeline fashion, rather than distributed in some other topology. Instead of using some other topologies like star, mesh, tree, it's better to use the pipeline fashion. Means sending data from one chunk server to the other, which is very nearest to that, so that there won't be any traffic and the data will be easily passed from one chunk to the other chunk. To avoid the bottlenecks and high latency links, each machine forwards the data to the closest machine in the network topology. So let's go to the next slide. Atomic record appends. Google file system provides atomic append operation called record append. Generally, in the traditional write operation, the client is going to specify the offset where the data should be written. But in the record append operation, the client specifies only the data, while the Google file system is going to choose the offset where the data should be appended. GFS may insert padding or record duplicates in between different record appends operations. Let's see why. Actually, record append operation is a kind of data mutation and it follows the control flow with only a little extra logic near the primary. Actually, the primary checks for during the data appending operation. The primary checks whether the appending operations is done in a particular, within the regular size of a chunk. It feels that it is going to exceed the 64 bit size, means then the primary is going to request the master for padding the size of the chunk, and whenever the appending fails at replica, client retires the operation. As a result, replicas of same chunks contains different data where the duplication is possible. Only the preferred application uses append instead of write. Let's go to the next slide. Snapshot. Snapshot is the enhanced operation given by this Google file system. These operations make a copy of file or directory tree almost instantaneously. Let's see the mechanism. When the master receives a snapshot request from a particular chunk, it checks for any leases on the chunk on the files it is about to be snapshot. Master waits for lease. If there is any lease, master waits for lease to be revoked or expired. Then the master locks the snapshot operation to the disk. Then it is going to apply the log record to its memory state by duplicating the metadata for the source file or directory. Master's operations. Namespace management and locking. We don't want to delay the other master's operations running, so we introduce the concepts here called locks. By using locks over the region of namespace to ensure serialization by allowing the multiple operations working for different masters, which are working for different masters. Here in GFS, we don't have a pre-directory data structure that lists all the files in that directory. GFS logically represents its namespace as lookup table lookup table mapping full path names to metadata. Each node in the namespace has a write or read key lock. Each master operations requires set of locks before it runs. Depending on the operation, master puts either a read lock or write lock. For example, if we want to create a new file, we put a read lock to all the way from the directory to the leaf node and write lock to a particular leaf node. If we want to write a data to that, we are going to put a read lock from starting of the directory to end of the directory till the leaf node, and are going to put a write lock on the leaf node. Locking schema allows concurrent mutation on the same directory. So while locking the schema, it allows we can make data mutations concurrently on the same directory. The main purpose of the locks here is to avoid a deadlock. Locks are acquired in a consistent total order to avoid deadlocks. Next slide. Replica placement. Replica placement serves primarily for two purposes: to maximize the data reliability and availability, and to maximize the maximum network bandwidth utilization. Why to spread chunk replicas across the racks? The following are the reasons. To make sure of chunk survivability. If the whole rack is damaged, to just make sure that the chunks are survived. To exploit aggregate read bandwidth of read traffic. In the especially for the read traffic to the chunks, we just need to exploit aggregate bandwidth of read traffic to make sure write traffic had to flow through multiple racks. Next slide. Creation, replica and rebalancing. Chunk replicas are created mainly for three reasons, that is chunk creation, re-replication, load balancing. Creation. When the master creates the chunk, it actually chooses where to keep the empty replicas. It is the empty replicas are kept based on the three reasons. We want to keep the chunk replication on below average disk space. We want to limit the number of recent creations on each chunk server. We want to spread replicas of chunk servers across the rack. Re-replication. Re-replicates a chunk as soon as the number of available replicas fall below a user specified goal. Here the priority concepts comes. Actually, the master gives priority for the chunks who have lost 2 replicas than a chunk who has lost 1 replica. And the master give priorities to re-replication for a chunk who has live files than a chunk who has stale files. Rebalancing. Periodically examines distribution and moves replicas from disk phase and load balancing. Actually, the master also rebalances the replicas by removing it if they are not in used. Next slide. Garbage collection. GFS doesn't immediately reclaim the available physical storage after the file is deleted. It actually waits for some time to delete the file. There are many advantages and disadvantages for this process also. Let's see the mechanism. First of all, to delete the file, the master renames the file to the hidden name on which it includes a deletion timestamp. To a regular scan, if a master sees this hidden file with a particular delete timestamp for more than 3 days means, then the master is going to delete it. Until then, in this 3 days, if we want to undelete it, we can just get it back by renaming it, or in this 3 days we can use it through a special name. The main advantages of it is it's simple and reliable in large scale distributed systems. It acts as a safety net against accidental deletion. If the file is deleted accidentally, it's fine, it stores for 3 days, so we can get it back. Disadvantages. When storage is tight, it is difficult to manage new chunks. When the storage is very tight, yes, it's difficult to manage the new chunks. So the master has a kind of logic for it. The master deletes the file. If the master deletes the file for the second time, after deleting it for the first time, if it deletes for the second time especially, then the file is going to be deleted right away. Stale replica detection. Stale means old. Chunk replicas become stale if chunk servers fails and misses the mutations to the chunk. So for this reason, to find the difference between the old replicas and the new replicas, the master has implemented a chunk version number. Chunk version number is used to find the difference between old and new chunks. How to find the updated chunk version? Okay, whenever the master grants a new lease on chunk, it should update the chunk version number. Master detects the chunk server has a stale replica when chunk server restarts and reposts its set of chunks. Master removes the stale replicas in a regular garbage collection. Fault tolerance. It is the challenges in the distributed system. The greatest challenge is designing the system dealing with the component failure. We keep the system highly available by mainly 2 strategies: fast recovery and replications. Fast recovery. We have designed the chunk server and master to recover itself from the failures. Chunk replication. Each chunk is replicated on multiple check servers on different tracks. Users can specify different levels for different parts of the file name system. Defaultly, we are going to replicate chunks in we are going to replicate chunks into 3 replicas. Moreover, master is replicated for reliability. Its operational log and checksum points are replicated on multiple mappings. Moreover, shadow master is the main thing to provide the read-only access to the file system when the primary server is down. Data integrity. Each chunk server uses checksuming to detect corruption of stored data. Checksums are kept in memory, that are stored separate from data. One read error is reported, that error is reported is to master. Master will replicate the chunk. Requester reads from other replicas. Diagnosis tools. Google File Server generates diagnosis tools about significant events and all RCP requests and replicas. Logs used for load testing and performance analyses. Here we are going to measure the GSF cluster setup for one master, using one master, 16 chunk servers, 16 clients, and a server machine connected to central switch by 100 Mbps Ethernet, switches connected with a 1 Gbps link, machine configuring dual 1.4 GHz, 2 GB of RAM, and 280 GB 5400 RPM disk, 100 Mbps full duplex Ethernet to switch, servers to one switch, client to the another switch, and switches are connected to the Ethernet. Well, this figure shows the aggregate read rate for n clients and the theoretical limit. Here in the right, n clients write simultaneously to n distinct files. Each client writes 1 GB data to a new file in series of 1 MB write. The aggregate write rate and its theoretical limit is shown in this figure. Record appends. This figure shows record append performance of n clients append simultaneously to single file. Performance is limited by network bandwidth of the chunk server that stores the last chunk of the file independent of number of files. Experiences. There are like two issues here, operational issue and technical issue. Operational issue, in under the operational issue, original design for the backend file system on the production systems, not with R&D tasks in mind. Under the technical issue, biggest problem were disk and Linux related. IDE protocol versions support that corrupt data silently. fsync function and mmap function also comes under the technical issues. Coming to the conclusions, GFS demonstrate how to support large-scale processing workloads on commodity hardware. So the first thing here is it is supporting a large-scale processing workloads, means heavy number of files, number of files. Here it is dealing with one of the challenges, scalability. The next one is designed to tolerate frequent component failures. Uh, Tolerance is also one of the challenges in the distributed systems, which this GFS is designed to tolerate frequent component failures. The next thing is optimized for use files that are mostly append and read. It is good for use files that are mostly to append and read. Go for simple solutions like single master. By using the single master, we are simplifying the whole design. And Google file system has met the Google storage needs, therefore good enough for them. Yeah, it has met the Google storage needs, and it is good enough for any file system. uh, I mean any sorry, it is good for anything to help the distributed applications. References, these are the references I took from, like, this is the first one is the research paper reference, the second one is the YouTube reference, third one is the Wikipedia reference, and fourth one is the other file which helped me to do this video. Thank you so much. If you have any doubts, you are feel free to ask me. Thank you so much.